All right, good morning. We've got the same light issue in here. You might have seen me pull it up and thought, oh no, uh-oh, I forgot to do that. That's okay, we're gonna do it together. Or if you did, that's awesome. So I left you with two exercises from the textbook that we're gonna just kind of work through. I am assuming that you did try it, even if you didn't. So go a little bit quicker through it, but we'll use it as review. Yeah. So what did we talk about last week? Last week we introduced variables, right? Different types of variables. And most importantly, I would say, right, a variable is either categorical or numerical. I guess I need a little bit more room than this. I jumped the gun. When we talk about data analysis, the variable that we're interested in is called the response variable, right? And so the response variable, just as a little bit of review before we jump in, the response variable is the variable of interest whereas the explanatory variables, potentially more than one, are collected with the hopes that they'll explain changes in the response variable. So the explanatory variable are collected with the hopes that they will help explain changes in the response. We introduced a lot of other things, of course, but those were kind of the key takeaways and the ones that are definitely going to haunt us throughout the rest of the term. Okay. And so I'll do this and this. To determine if a variable is categorical or numerical, right, we used kind of the argument, okay, if it makes sense to talk about the average, I'm going to treat it as numerical. And if I want to report on the counts or percentages, then I'll treat it as categorical, right? And a response variable can be either categorical or numerical, okay? And an explanatory variable can be either categorical or numerical. Okay? I think I said that we would only consider numerical response variables for the scatter plots for regression analysis. But then I had a look in the textbook and it looks like we might be able to sneak in a categorical response as well. So that's exciting, right? Lucky us. So that's pretty cool. We'll just touch on it just so you've seen it, so it's not so scary. Which I feel like is what this course is mostly about, right? So you've seen it, so it's not so scary. Okay. So we talked about a lot of other things, but we've got these exercises to help us through. So I guess I'll read you this blurb. Researchers studying the relationship between honesty, age, and self-control conducted an experiment, which we'll talk more about today, on 160 children between the ages of 5 and 15. Participants reported their age, sex, and whether they were an only child or not. Okay. The researchers asked each child to toss a fair coin in private and to record the outcome. So I guess it's a white side or a black side of a coin. Seems kind of weird. Usually it's heads or tails, but whatever. Seems elaborate, unnecessarily elaborate, but whatever. So they have to record the outcome on a paper sheet and said they would only reward children who report that the white side landed up or tails or whatever. Okay. Imagine thinking of this study. They came up with this study. Weird. So clearly someone did. It was 2011, even more kind of disturbing. But, oh, thanks. If we have to identify the main research question of the study, so what were they trying to kind of get to the bottom of with this experiment, right? That's a good thing to think about. You'll be starting from the other way, right? With your research projects, you have to come up with a research question and then cook up some way to collect data to analyze it, right? And so, but it's nice to kind of approach it from in reverse, right? Kind of boil it down. So what would you say? And there are kind of lots of ways you could phrase it, but I usually just steal the answers from the blurb whenever I can, okay? And so they were studying the relationship between honesty, age, and self-control, okay? And so, right, is there a relationship between honesty and age? I think self-control might be kind of overlooked a little bit, kind of baked into the honesty portion, in my opinion, right? But however you want to phrase it is fine, okay? And so let's see here. Is there a relationship between age and honesty? Right. We're hoping that as the kids get older, they're going to be more honest. I almost kind of suspect it goes the other way because they understand kind of the reward system. But what do I know? Do you have a question? Mm. It does. So we're going to call those explanatory variables, right? So if we don't find anything with age, which is our first kind of check-in point, right? We think maybe age is the overarching variable that's going to affect honesty. But then we've collected things like sex, things like whether they're only child or not. And so if we don't find anything with age, then we can say, okay, well, how about gender? Or how about if they're an only child or not, right? And so these, I would say, are, well, age is an explanatory variable, the first one that we're interested in. And then we can consider sex and whether they're an only child or not as other explanatory variables.
So we do not add that, because that, how does age, sex, and child's ability to choose?
Well, that's fancier, isn't it? It is. No, that's correct. That's correct. It's more involved than mine. I was trying to kind of condense it as tight as I could. Yours involves more variables, which would involve a deeper analysis and kind of a higher level analysis. But that is what they're saying. So
okay,
yeah.
Okay. That's my question.
Yeah. But you're totally right. If you're incorporating all those variables, as long as you're kind of relating it back to the response variable being honesty, then that's, yeah, you got it.
You don't have data stated like in that part C, we usually talk about it, I just made it that there's no results for dating, so whether or not they're putting children.
Let me read it. It's so long. Can I just write down what I was, so I was going to write that this is the response. And this is the explanatory variable. But totally fine to look at the other explanatory variables as well. The main one being the response, right? What's the response variable that we're interested in? Let's do B and then I'll get to C. Seems reasonable. Who are the subjects in this study and how many are included? Well, there were 160 children between the ages of 5 and 15. And so that's your answer. Can I just copy this? Now see. Oh, which means from before and your sample size is 160. From last week. Kind of nudging in some review there. Okay. The study's findings can be summarized as follows. Half the students were explicitly told not to cheat and others were not given any explicit instructions. In the no instruction group, the probability of cheating was found to be uniform, so just kind of doesn't matter, across the groups based on child's characteristics, kind of general. Presumably they started with age and then went to gender and all those things. In the group that was explicitly told to not cheat, girls were less likely to cheat. And while the rate of cheating didn't vary by age for boys, it decreased with age for girls. So they did see a relationship in that subgroup of the girls. How many variables were recorded for each subject in the study in order to conclude these findings? And so what it's asking for is if you have your child number 1, 2, 3, blah, blah, blah. If you imagine your spreadsheet, I'll clean this up. Child number, it's observation number 1, 2, 3, but maybe it's nicer to call them child. I don't know. So think about the columns. What columns would we have in our spreadsheet? Well, we know we have age, right? Can I kind of cross these off somehow? Let's see here. Reported their age, their sex, whether they're an only child or not. That's going to be usually a 0-1 situation. So even though we record them as numbers, right? 0 if they're not an only child and 1 if they are an only child, right? Making it binary. We do that a lot and we call them dummy variables, right? And so we kind of flick the switch on if it's a yes and then turn it off if it's a no, right? Because you can boil it down into a yes-no situation. Okay, and so, and we'll see that a lot more, right? But I'll make a note here that this is going to be kind of a 0 or 1, right? Turning it into binary, right? Yes, no, or I guess no, yes in that situation, 0, 1. So only child, okay. only child or not. We could record the outcome. Right? What was, yeah, yeah, so let's do that one. That one's more obvious first. So, were they told not to cheat? I'll do a told question mark, right? Told not to cheat. Okay. Again, I'm going to report that as a 0 or a 1. Right? No, they were not explicitly told to cheat, or 1, yes, they were told that they're not allowed to cheat, right? And so, right. And so here, half the children were explicitly told. I'll write this as told here. We'll summarize that as told. A lot of the time we boil down our variables because often you're going to end up programming these variables, and you don't want to have crazy long names for these variables, right? And so the shorter the variable, the better. Is that in the ceiling? Or oh, applause, I think. I hear what I want to hear. Last term, yeah, it was in the e-building. And for my 8 a.m. class, the class behind me kept watching movies in the morning. And it was really hard to teach math when you know that the other group is watching a movie. So hopefully that's not the same this term. Okay, so we've got whether they were told or not. Okay, we don't have the response variable on here. How do we record the response variable, right? We've got the reported outcome, right? Heads or tails from flipping a coin. I don't know why it's white or black. I guess if they're young, if they're 5 years old, heads, tails is kind of hard. That makes sense. Right, but the recorded outcome, or sorry, the reported outcome might be different from the actual outcome, right? And that's going to be how we judge honesty, right? If there's a difference between the reported outcome and the actual outcome, so someone would have to be watching to see what happened, right? That's not stated anywhere, right? But how else would we measure honesty, right? And so then we need the reported outcome and the actual outcome. You could. Or cheated, right? It's totally fine. Yeah, yeah. If you do that, you wouldn't be able to kind of summarize. Maybe you're interested in, what was reported, right? We know that it should be overall kind of with 160 participants, we're expecting kind of a 50-50 split, right? In black coin tosses and white coin tosses, right? Because we know how coin tosses behave, right? And so that might be interesting as well. But yeah, you could boil this down if you've kind of got that as one. Totally fine. Yeah. Yeah, because mine, I would have to add or construct a new column over here on honesty. I'm running out of space here. Uh-oh, that's gonna be hard to move over. Or let's see here. Right, I would have to generate an additional column to indicate whether they were honest or not. which is kind of what you're skipping to get to the chase. Right. Okay. So how many variables are there? Let's do just the blue ones, right? If you lump these into this one here, that's fine. But let's do 1, 2, 3, 4, 5, 6. And then I would generate the honesty variable, right? But not necessarily collect it, right? We're allowed to generate variables later, right, in our analysis. Which ones are numerical? Only age, right? All the other ones are categorical, even though we're going to record them as 0, 1s, right? Which are numbers, but those numbers represent categories, right? Yes, no. So this is numerical, and these are categorical. Nice. This here is what makes it so hard to mark, because as long as you're kind of using sound logic, right? If you had created a cheated variable, that's great, that's cool, right? Whereas I would break it down into the reported and actual, because I like to have more information, right? You've kind of taken that into account already, but right, if I'm marking, I can be kind of swayed either way. Same thing here, right? If you had a longer description of what the study is about, that's cool, that's great, right? But as long as the honesty is the response variable, I'm happy. And that takes getting used to, especially coming from math, right? We like concrete things. Oh yeah, I've saved this. I'll bring this in because I like it better than anything else in the textbook. So I'll put her there. Just zoom in a little bit. Okay. Researchers studying the effect of antibiotic treatment for acute sinusitis compared to symptomatic treatments randomly assigned 166 adults diagnosed with acute sinusitis to one of two groups, either the treatment or the control, which we're going to see today, right, is kind of a basic experiment. Yeah. Study participants received either a 10-day course of amoxicillin, an antibiotic, or a placebo, which we're going to talk about today. But I think we all kind of have heard about placebos and the placebo effect and that kind of thing if you've watched any medical drama. But what if they get the placebo? Or a placebo similar in appearance and taste. And so the placebo consisted of symptomatic treatments such as acetaminophen, nasal decongestants, etc. And at the end of a 10-day period, patients were asked if they experienced improvements in symptoms. I would say improvements in symptoms is really hard to measure, right? And you'd be relying on a yes and no type of categorical outcome, right? So the improvement, either no improvement or yes, there was improvement, but we don't know what that improvement was, right? Could just be time, right? That kind of thing. And so the distribution of the responses is summarized below. So we've got the group, they're either in the control group or the treatment group. They've been randomly assigned to be in the control group or the treatment group. And then 10 days go by and there is either no improvement or some improvement. Okay. What percent of patients in the treatment group experienced improvement in their symptoms? So I'll do A down here. So the percent of patients in the treatment group. Okay. So now I'm only interested in the treatment group, 19 out of whatever the total is. All right. And so the total here, let's see here, is what? 85. Thank you. And so 19 out of 85. I'll bust out my trusty calculator. Duh. That was a test. Thanks. $66 out of 85 puts me at roughly 0.7764705882. It does ask for the percentage, or 77.6, let's say 5%. They would probably round to a whole number, but I want you to keep some decimal places. You don't want to do any rounding here, because then when you convert it to a percentage, right, I want to see like 1 or 2. I'm not committing. What percent experienced improvement in symptoms in the control group? What do we have for a 16 plus 65, 81 total? And 65 is similar to 66, but the totals are different. 65 over 81, whoops. 0.80. Okay, I didn't do that wrong. Okay, probably a bad treatment. Why? Bless you. You need to be in the control group, it looks like. Because they had a higher percentage of improvement. Let's do 2.5 to be consistent. Percent. That's probably not great if you have spent a ton of money developing this new drug, right? Because this was for the treatment and this was for the control. It can be. Kind of depends on the situation. I think sinusitis is one of those where you don't want to be not treating it at all for 10 days, probably. Seems ethically borderline. And so I think that's probably the reason, right? We have to deal with those pesky ethics, right? And so, but if that's kind of your baseline, then, right, if you're saying that someone has sinusitis, then you would prescribe acetaminophen or whatever, then you can use that as your control. Usually though, the placebo is just a sugar pill or something like that, you know, or go through the motions. In the textbook, they even talk about kind of doing fake surgeries. Ethics comes into play there, right? But if you're kind of judging surgeries or this new kind of, what do you compare it to, right? And so usually we don't do fake surgeries because that's bad. And the risks outweigh the rewards, but right. So here, there is a difference in these percentages, but the goal of this course is to develop techniques to determine if there's a significant difference, right? And so that's what statistics is all about, right? And so at best, we would be able to say, oh, there's no significant difference between the treatment group and the control group outcomes, right? We can't, or we probably wouldn't care about the control being significantly better than the treatment, right? That's not something that we're after. And so, so that's what we're building towards, right? Is being able to compare these numbers and say, okay, well, with this sample size, right, then these are not significantly different from each other. We're not there yet, but nice to see. Okay. In which group did a higher percentage of patients experience improvement in symptoms? Well, we already talked about it. The control group. Like we talked about, she's got these subtle ways of getting to the point, kind of developing the idea. But your findings so far might suggest a real difference in the effectiveness of antibiotic and placebo treatments for improving symptoms of sinusitis, right? So looking at these numbers, they are different, right? This is not the only possible conclusion. What's the one other possible explanation for the observed difference between the percentages of patients who experienced improvements in symptoms? Well, that would be random chance alone, right? And so that's what we're going to be getting at is, okay, well, this difference could have just happened by random chance alone. And in fact, they are essentially the same, right? If I asked each of you to flip a coin 100 times, even though 100 is a lot of times, right? And record your results, right? Would I expect every single one of you to have a 50-50 outcome? No. Overall, though, I would, right? Kind of if I blur the lines, right? Then I would, okay? And so here, differences may be due to random chance. Finally, what are the explanatory and response variables in this study? Well, first, what are the variables? I only have information on two variables, right? The group that they were assigned to and the improvement that we saw, or they saw, or reported rather. I know, picky. That's stats. Right? And so both of these variables, right? The group is a variable, the improvement is a variable, and they're both categorical, right? So I have two categorical variables, and usually we report those variables in what we call a two-way table. It looks like this, right? Or a contingency table. Okay, but which one is the response variable? Now, the response variable is the one we're most interested in, right? We're most interested in the improvement, and we hope that the group that they were assigned to would help explain changes in that response, right? And so for us, oops, zoom, pinch. The explanatory variable is going to be what group they were in, and the response is going to be the improvement. And both of these are categorical. Last day, right, we saw the explanatory and the response variables for numerical data. Whoops. But then usually we visualize it with a scatter plot, right, from last week. That's when we had the response and the explanatory variable here. And this is when it's numerical. Differences between two categorical variables and two numerical variables, just so you have it. And maybe I'll scooch this up here. Sure. There. Okay. Why did I do that? Do I want to start? I'll start today on a fresh page anyways. Let me bump that back down there. Lots of room. Start today. I'm going for like 40 minutes, I think. Time. What a funny thing. Nice to warm up though. Any questions about those? Kind of questions about the questions? No. Okay. You can, again, I get sloppy, but that's the control versus the treatment, which you can summarize as the group. But this is why I have to read your responses, right? Because there's so many ways that I'm fine with that, right? That's difficult as a student, but if you're ever unsure, just ask. Okay. Wait. So chapter 2 is on study design. Study design is going to be kind of data collection. How do I prepare to collect my data? Right. And so this is going to be on data collection. Kind of what should you do, do's and don'ts of data collection, different types of data collection, but also preparing to collect data. What you'll find later in the course is, depending on what the end analysis that you want to be reporting is, that'll determine how you should collect your data, right? And so we'll kind of revisit it where you need to think about, okay, well, if I want to do a 2-sample t-test, which doesn't mean anything now, but it will, right? If I want to do a 2-sample t-test, I need to have my variables set up in this way, right? I need my data to be set up in a certain way. And we can manipulate data but kind of the structure of the data determines what you can do with it. So data collection, I think I mentioned it before, is one of those funny things where in a typical stats course, I usually say, okay, data collection, it's intricate, it's difficult to do properly, and you should probably just hire someone who knows what they're doing. But you guys actually do have to collect your own data, and so we need to spend a little bit of time talking about how to do that. Okay, and so data collection, again, broad strokes. We have 2 different arms of data collection. Okay. The first one is we can have observational data. Taking a clue from the word, right? That's when we sit back, relax, and observe information, right? We might have to measure it and things like that, but we're not manipulating anything, right? Which is the other arm of data collection, which is experiments. So kind of 2 main ways that we can collect data. They are similar in some ways, and the analyses are similar, sometimes indistinguishable, okay? But there's kind of different terminology for experiments versus observational data. One of the main things is if you want to report causality, right? This causes a change in this. The only way that you can do that is with an experiment. Okay? Because in an experiment, as you can probably imagine, right? You've got your lab coat on and you're tinkering with I don't know, whatever chemicals or whatever you're doing, right? You're controlling a lot of these factors, right? And so that's the only way that you would be able to report, hey, when I did this, it caused a change in my response variable, right? And so experiments, we'll do it in pink because it's so important. Experiments are the only way to establish causality. I'll say, since we control hopefully all the factors, if you start thinking about even a simple experiment and you have to control all the factors, right? Including room temperature, time of day, if that makes a difference, right? That's going to be really difficult, but kind of within reason, right? So experiments are the only way to establish causality, assuming we have controlled most factors. Right. I guess I should finish it. That could affect the response. Could affect the response. This is how run-on sentences are made. Experiments are the only way to establish causality, assuming we have controlled most factors that could affect the response. Whereas observational data, we can establish a relationship, right? We can observe a relationship. And so here, less important, but we can establish a relationship, like we said last day, and we saw last day, We can establish a relationship, but not causality. Thinking about the presentations, the wet presentations in December, right? There was a lot of observational data, right? You go out to a reservoir, you collect information, right? You're measuring it, but you're really just observing it. You're not manipulating the water in any way. I would say there was room for an experiment, right? There was like a water tank filtration system, right? So there would be room to build an experiment. I don't think that they had explicitly. They had just observed information, but there was kind of room to do an experiment there. But we can talk about that. I know that's a ways off, I guess. Not until December for you guys. Ugh, scary. Okay. For any data collection, the one thing that we're trying to control for, and I know I'm using control in a different way, sort of, is bias, right? We want to make sure that our sample is representative of the population that it came from. Okay? And so for all data collection, oops. For all data collection, we want to ensure that our sample is representative of the population that it came from. We want to ensure the sample is representative of the population it came from. All of our techniques rely on the sample representing the population, right? I can't take a sample of, well, I can't use this room as a sample because the majority of you are in one cohort, right? And so the wet department doesn't necessarily represent all students at Okanagan College, for example, if that's what I want to learn about. You are students at Okanagan College, but there's a chance that you're kind of more similar because you chose the same program and you've been kind of working together, groupthink and all that. Right? And so, right, and so if I want to talk about and generalize my conclusions about all students at Okanagan College, then I would have to randomly sample students from Okanagan College. Okay? And so the best way to do that, the best way to ensure a representative sample, is by, randomly selecting data. Or I guess observations, but participants. Sure. Randomly selecting, maybe not data, but observations. On the flip side, we're trying to avoid bias, right? And so good sampling avoids bias. I guess at some point, I started saying sampling instead of data collection. Cheeky. But that's what we're doing, right? Sampling or good data collection. Avoids bias. What is bias? We have an intuitive understanding of bias, but the technical definition of bias is systematically favoring one outcome, right? And so bias is systematically favoring one outcome. I guess it could be one or more. One or more outcomes. So that's bias, right? And the best way to avoid that is by randomly sampling. Okay? There are lots of ways to randomly sample, but before we go into that, I'm going to start by talking about how we collect observational data, and then we'll talk about how do we collect experimental data and how do we design experiments. So let's talk about observational data collection. There are kind of four main ways that we can collect observational data, right? And so the first one, so there are many more, right, designs that we could use, but there are four main designs. There are four main designs we could use. First one is simple random sampling, which is what I would encourage you to use if you can, right? And usually that sentence ends with if you can afford it, because it can be really expensive, okay? And so simple random sampling is usually abbreviated SRS. Okay? Simple random sampling is when every individual in your population has the same probability of being selected into the sample, okay? Meaning no individual in your population has a higher probability of being selected, right? That's kind of a lofty technical description, right? And so let's write that down. Each individual in the population has the same probability of being selected into the sample. That doesn't mean you are selected into the sample. It just means that if I have, I don't know, 10,000 students, right? The probability that any one student is being selected into the sample is 1 in 10,000 or 30 in 10,000 or whatever sample size you're selecting. Right? I want to outline the different types of sampling, and then I want to talk about, well, how can we make a random sample, right? What are some techniques that we have? The reason for that is our analysis techniques are really only going to kind of work if you have a simple random sample, right? So we're going to assume that you've collected a simple random sample. Of course, the extensions for the others is not, crazy. And lucky for you, I teach a course on it at UBCO with the extension of how do you analyze data from a, for example, stratified random sample. So we're not going to talk about the analysis in this course, but if you find yourself, right, you've collected data and you used a stratified random sample, then we can talk about the analysis techniques, which again are not a huge leap from what we're going to learn, but just know that they're a little bit different. A stratified random sample, an SRS, no. SRS is only for the simple random sample. Stratified random sample, hey, I'm giving it away, or maybe I'm not, I don't know. The stratified random sample is, if I say strata, right, you're probably going to think about an apartment building, right? Then you live in a strata. What does that mean? It means that you've got a group of similar observations, right? Similar things in your population. Okay. And so if the population can be split into strata, okay, if the population can be split into strata, where strata is a group of homogeneous things, okay, or homogeneous observations, a group of homogeneous or similar observations. I guess I should say individuals or kind of measurements. I'm using individuals because it's easier to think about people than it is to think about measurements of water samples, right? And so I'm using it kind of loosely, a group of homogeneous individuals, right? And so some similar characteristics. What we can do is we would need some identifier in your data, right? Or for your population. And so maybe the program you're in, right, is a strata. Wet students are a strata, nursing students are a strata, science students are a strata, right? They're all kind of similar individuals. And whether you think that or not, I don't know, but let's assume that they are, right? Then what would we do? Then we could take a random sample within each strata. So you wouldn't need to look at all the strata, but it would also ensure that each strata is being represented, right? If you think that that's important. So if the population can be split into strata, we could randomly sample I don't mean that in the kind of colloquial way. I just randomly sample. No, sample randomly within each strata is what I mean, not randomly sample. Hopefully that's clear. We could randomly sample each strata. Right? So that we have a little tiny sample from each strata to ensure that all stratas are represented. To ensure all strata are represented. That's especially a concern if you have some small strata or stratums. Stratas? Stratas. Stratum is singular, and strata is plural. Strata. You think about BC, right? If you just randomly sample people from BC, where do you think most of those observations are going to come from? Probably the lower mainland, a little bit more out here, but you're going to have a hard time capturing people who live up north, right? Because there aren't very many of them, right? And also might be hard to contact, but we're avoiding that, right? Just the fact that there are so few people in comparison who live up north than do in the lower mainland, right? They would be kind of drowned out by the lower mainland data, right? We all would. Our voices need to be heard. So what do? We can say, okay, I'm going to split these into strata, right? Obviously, I want to have kind of information from the lower mainland because they are a huge part of our population, right? But I also want to make sure that I have information from people who live in the north, people who live in the Kootenays, people who live here, right? And so, so then stratification would work. And so, but stratified random sampling is just random sampling within each strata. And then you smush all that data together and you have some identifier that says which strata they came from, right? But then you can use that as your entire sample. Okay. I know I still haven't talked about how do we randomly sample. Watch till the end. My whole class is clickbait. You won't believe what happens next. No, I want to talk about the next one, which is cluster sampling. Okay, cluster sampling is similar, but a cluster is not necessarily similar things. Usually they're kind of heterogeneous individuals. So a cluster heterogeneous individuals. Observations. Okay. So not similar necessarily. If we want to make the argument that what program you're in, right, doesn't make you similar, right, it makes you clusters, right, then we could use cluster sampling. Your clusters, because you're all individuals, right, and maybe you are similar, then you could call them strata, and if you consider them not similar, then you would consider them clusters. Again, one of those, well, whatever way you argue it, it's fine by me, right? But you have to use the right argument. So a cluster sampling is different because then what we do is we randomly select clusters. Okay? So I use a random mechanism to pick clusters, but then I sample everyone in those clusters. Okay? And so we randomly select clusters and sample all individuals in those clusters. So here, this is the one that I've been saving because it came from another textbook that I really like this version, right, of the visual. And so here we have, so this is stratified sampling and this is cluster sampling. Okay. Notice that each block here are all the same color, right? And so here we have homogeneous individuals, whatever, right? Homogeneous groups versus here in the cluster sampling, right? I have heterogeneous groups. I have some, I don't know, brown, blue, purple, mauve, green, right? Individuals. Whereas here, these are all, I would say brown, I guess. Oh, they really went for it with the different colors. But this one, right? All these individuals are blue, right? Kind of similar observations. Whereas here, right, I have these heterogeneous groups. That's the difference, or the difference between clusters and strata. Strata, clusters. Okay. Then stratified sampling, I select randomly individuals from each group. Right? Often we do the same number of observations. There's lots of different techniques, but here they've done 2 observations, randomly select 3, randomly select 2, randomly select 3, 2, 3, whatever. And so, but usually we do a similar count in each group. And then you would smush all those colored in dots and that would make up your sample. You'd want to make note in your data set, right, which group they came from, right? Are you in the blue man group or the green man group? All right.
Just want to bias though by having numbers.
It depends. Usually you would try to have the same number, but if red is kind of representing a huge group, then you might want to bump up those numbers. There's kind of different ways that you could do it, argue it. Here they've used different numbers just to see that they don't have to be the same. Cluster sampling is different, right? Here I've randomly selected these 2 clusters, but then I sample all the individuals in those clusters, right? So visually, that's what it looks like. And then your data set would be all those dots, I guess, smushed together. Right? Not getting information from these 4 clusters, but we assume that these 2 randomly selected clusters are representative of the population. If you are concerned that they're not, right, then maybe cluster sampling isn't the right way to go. Right? Then maybe we should do stratified sampling. Neighborhoods, for example, within a city, right, can be very different, right, depending on what city you're in, especially, right? There are some very nice neighborhoods and some very not nice neighborhoods and something in between. And so then cluster sampling might not make too much sense. But it all depends. You're kind of off the hook. You don't need to do stratified random sampling or cluster sampling, because like I said, our techniques really only apply to simple random sampling, right, to start. So all we will think about in this course is simple random sampling, but we should know what it looks like. The last one is kind of the most extreme of them all, is called multi-stage sampling. Multi-stage sampling is cluster sampling followed by stratified random sampling. Okay, and so in each cluster, you separate them into strata, and then you randomly sample within each strata of the clusters. It's not something that I would encourage you to do. You can, right? But it exists. But it's cluster sampling. But beyond knowing what it is, I don't want to talk about it because we've got more important things. Oh, we laid floor this weekend and my hamstrings are killing me. Which is weird, right? Because anyways, I don't know. I can't explain it. But it's clusters. So multi-stage sampling is cluster sampling followed by stratified sampling. Stratified sampling within the clusters. One example would be if you work at a market research firm and you're trying to kind of gather provincial information, then, right, cost is an issue, right? Gathering all this information, it costs money. And so then I might say, okay, I'm going to treat each area of the province as a cluster. Okay? But then each area of the province has kind of different sub areas, right? And so then I can create strata within the clusters and randomly sample within each of those strata, right? Not taking the entire cluster. But like I said, that's way too much to keep track of. So I'll end it there with the definition. Okay. How do we randomly sample? How do you make sure that your sample is randomly selected? Okay. So how? There are many, many ways. How do we select a random sample? Right? All of these sampling techniques relied on, okay, you either select a random sample from the population, that's simple random sampling, or stratified random sampling, you select a random sample within each of the strata, or cluster sampling, you select clusters, you randomly select clusters, sample everyone in those clusters, right? Random sampling is haunting us. So how do we select a random sample? The most basic way is you can flip a coin. That's going to be very tedious, right? Yes, you're in, or tails, you're in, heads, you're out, right? You're in my sample, you're in my sample, you're out, you're in my sample. What am I relying on? I'm relying on a random mechanism or a random process, right? Flipping a coin is a random process. There's only two outcomes. I know it could land on its, I know, we ignore that. Results, but it could land on its side. Yeah. And we also assume that there's a 50-50 chance, right, of heads and tails, which is also up for debate, right? And so, but for our purposes, good enough, right? What does that mean? every individual, if we consider this room, the population, if I flip a coin, I go through the rows and I flip a coin, you're in my sample, you're not in my sample, you're in my sample, right? Every individual has the same probability, right? 50-50 chance of being selected into the sample, which, dun, 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 where is it? Where did I? Oh, here. Each individual in the population has the same probability of being selected into the sample, right? 0.5, 0.5, 0.5. It's also just random sampling. That seems tedious. That's another thing we could do. We used to, so even in my time teaching, I used to, there's a random of, or a table of random digits. What would you have to do? Again, relying on a random mechanism, right, or a random process. If we, again, consider this room our population, right? I go through and I get 1, 2, 3, I assign you some identifying number, right? And then in my table of random digits, which is exactly as it sounds, it's just a table of random digits going in rows like this, right? Then I have, I think 30 students, supposed to have 30 in here, right? And so then I would move in groups of 2, right? Because if I move in groups of 1, I would only be able to select the single digit people if I started here, 1, 2, 3, blah, 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 right? So I move in groups of 2, and if I find a number that's one of the people that I could pick, you're in my sample. That also seems elaborate. I'm not writing those down. But what's another way I could do it? Rock, paper, scissors, sure. But then you're kind of yeah, if you win rock, paper, scissors, then sure, you're in my sample. That's good. Typically now what we do is we do assume that we have some list of everyone in our population. That's not necessarily the case all the time, right? But if you're the registrar's office, you have a list of all students at the college, and it's relatively easy to think about and do, okay? So if I have a list of everyone in my population, okay, then again, I would assign them numbers, right? Just some identifying number. And then I can use a random number generator, okay, and generate a list of random numbers and attach that of the same length. Okay, I'm thinking in Excel here, right? And so because you've got a long list of you've got a huge population, right? And so then you attach a random number to your list of or your population. Then you can sort those random numbers and you pick the first 30 or first 40 or whatever sample size you want, okay? And so that's typically how winners are chosen if you're in a draw, right? You did a survey and you know there's a draw at the end. That's usually how winners are selected, right? But also how we randomly sample, okay? And so there's something else I wanted to say there. That's harder if we don't have the entire population, right? But we can kind of imagine having some idea of the population, right? Maybe split it up into areas. I'm thinking about, let's think about a pond even, right? You want to randomly sample a pond, right? You could break it up into areas and randomly select those areas. Okay. So there's lots of ways to collect a random sample. Humans are very, very bad at random. we're just inherently bad at creating random numbers. And so there's huge debate because a random number generator can't be truly random. We had to program it, right, to generate random numbers. And when I was working in industry, random.org claimed to be the most random number generator. Yes. So hopefully that's still the case. I'll have to look into it. I haven't needed to collect a random sample in a long time. And so, but you can go down that rabbit hole and find the most random number generator. But of course, Excel has a random function. It's not very good. It's good enough, but it's, it's got flaws. How do we determine if it's good? Well, that's a side, whatever. Okay, let's write down. How do we select a random sample? I guess I'd be doing a disservice if I didn't say there are many ways, but most commonly, right? We talked about many ways, but most commonly, we use a random number generator. Which would involve first assign an identifying number to everyone in the population. An identifying number to everyone in the population. Right. More or less reasonable, right? But if you can kind of frame it in a way where you're able to assign some identifying number to your population, then that's a good place to start, right? Even if your population feels infinite. So you assign an identifying number to everyone in the population, and then generate a list of random numbers the same length as your population, right? Generate a list of random numbers you could see random.org. Should see if it still exists. It does. I think so too. I mean, how could it fail? They're the most random. Okay, verifying I'm human. Random.org offers true random numbers to anyone on the internet. Wow. Wow, wow, wow. So they used to claim that they were the most random number generator, but what's the fuss about true randomness? Anyways. You could use the random number generator in Excel. Yeah. I'll follow it up here. Or use Excel or some other random number generator. Okay. So generate a list of random numbers the same length as your population. The same length as your population. You can avoid repeated numbers in your random numbers or you can allow it. That's totally, it doesn't really matter as long as they're random. Okay. Then you can attach that list of random numbers to your population. So what I'm imagining is a spreadsheet, right? And you've got your entire population with some identifying number, right? And then, or maybe you don't even need the identifying number in this case. I was kind of doing a hodgepodge of two things, I guess. It doesn't hurt. I'll add in here. Not needed. Oops. Okay. So if I was merging two things. That's okay. You can assign a random or a number to everyone. Okay, so you've got a list of random numbers. You're going to attach it to your population. Copy pasta. Attach the list of random numbers to your population. Whoops. Usually we sort. Doesn't really matter how you want to sort it, right? Smallest to largest, largest to smallest. But usually that's how we do it is we sort the random numbers and then you can select the first 20. If you want a sample size of 20, for example, you can select the middle 20, but that's more annoying. Because of the random numbers, it doesn't matter where you take this chunk of 20, right? You can rely on those random numbers to have done the shuffle for you. So sort the random numbers and select the first n individuals. N is your sample size, right? First or last or last or middle, right? You just take a chunk of n individuals. Usually I just take the first n. And then you have your sample. One thing is if you're using the random number generator in Excel, then every time that you kind of hit enter and you do something in Excel, it'll generate new random numbers. So in that case, you'll want to copy and paste special just the values so that you have a copy of the random numbers, right? Otherwise, it'll keep changing on you. That's what I mean. So here, I'll do an Excel note. The random function regenerates after each calculation. So you can generate a list of random numbers and then you can copy. So copy, paste special, and just do the values to keep a static copy. Otherwise, it'll keep changing on you. There's also a sample function in Excel, right? It's a little bit finicky and way too clunky in my opinion. I think it has to have zeros and ones, which is kind of weird. Why can't it just do it? But it's okay. And so I'll give you an exercise to play around with that. But so there are lots of ways to select a random sample. I'll do a random bracket. So I'm pretty sure it's called random. You have to give it some arguments, but generates random numbers. Okay.
After what calculation?
After each calculation, so copy, paste special values to keep a static copy. Okay. Time flies. You're having fun. Ready to talk about experiments? Yeah. So, well, any questions about kind of observational data? So the main takeaway is as long as you're sampling randomly somehow, right, then that's going to be good, and it will avoid bias, you know, just by random sampling alone. Or at least enough to argue that you can avoid the bias, right? So experiments. We've already talked about experiments. Right? There are kind of, again, 4 components of experiments to keep track of. Okay. The first component, or I should introduce it. So in experiments, we incorporate 4 things. The first is we want to control, right? And so you don't want to do an experiment without some baseline to judge it against, right? We've already seen that with our treatment and control groups, and that control can kind of take the shape of many things, but usually a placebo of some sort. And so we want to control. We want to have a baseline, let's call it, to compare our treatment to. To compare our treatment to. Usually a placebo. Usually this is done with a placebo. The placebo, right? We've already talked about the placebo, but what's interesting about the placebo is the placebo effect kind of has been documented to be real in a lot of instances. Okay, and so right, there is improvement just by thinking that you are going to improve, right? And so that's pretty interesting, but depends on what you want to study. If you're studying tomato plants, for example, and you want to measure the yield of tomatoes, right? then your control group would probably just be a group of plants that they don't get a special fertilizer, and maybe they just get a normal amount of water, or maybe just a baseline amount of sunlight, right? There's no kind of placebo, but you do have some control, something to measure against, right? And so it's not always a placebo, but you do need a control group. Yeah. You want to randomly assign treatments, right? And so randomization is another thing that we need to incorporate. Randomization, right? We already talked about how do I randomly select people? How do I randomly assign treatments? Again, you can generate a list of random numbers just going between 0 and 1, right? And if it's a 0, you don't get the treatment. If it's a 1, you get the treatment. Okay. We do, trying to not say control because it means something else in this context, but we do like to ensure that we have roughly the same amount of observations in our control group as our treatment group, right? So we do try to have an equal number, but how they're selected is by randomization. Okay, so we randomly assign participants. If it's an experiment, we call them participants usually, or subjects, or but I think it's kind of cute to think of tomato plants as participants, but doesn't really make sense, but it's cute. So we randomly assign participants to the control or treatment group. You could have more than one treatment, so I'll do plural groups, but for us, we'll focus on just control in a treatment group. So you're randomly selecting who's going to get what treatment, whether it's the control or the actual treatment. And here I'll say we usually split participants evenly across the groups. Right. Which means if you have it boiled down to a control group and a treatment group, right, then you could randomly select 10 out of 20 people to be in your treatment group. And then if you're not in the treatment group, you're in the control group. Right? Third thing that we need to incorporate is replication, right? I don't want to have just one control tomato plant. I probably want to have a replicate number of tomato plants, right? I don't want to collect information on one individual, for example. I want to collect information on a group of individuals. Okay. So replication, right? Assign the treatment. Assign the treatment. If I use treatment as I won't, sorry, forget I said it. Assign the treatment or control to more than one participant. Probably wouldn't forget that, right? You want to have kind of boosted numbers. There's a really interesting kind of caution in the textbook, because now we get all this social media, and a lot of videos are relying on anecdotal evidence, right? And so for example, what was one extreme? Someone goes on like a raw diet, they only eat raw meat or whatever, and it really worked for them, right? That's anecdotal evidence, right? You should probably do a study and an experiment if you want to rely on those results for yourself, right? But anecdotal evidence is kind of popping up more and more, and we need to be really aware of it, right? Because these one-offs are, yeah, they're kind of interesting, but they're not proof that something works, right? And so I don't know where that falls in here. It's more of a word of caution. Okay? So anecdotal evidence is bad. It's interesting, but it's not useful, right? So replication, right? Do more than one measurement in each of the groups. Okay? And the fourth one, which is kind of, I'll say optional. It depends on the depth of your experiment. But the fourth one is blocking. Okay. Blocking is if there's some variable that you think might contribute to changes in the response, but it's not something that you want to really be reporting on, right? You just think it could influence the response, right? Then you would treat it as a block. Okay. And so if you suspect a variable, right, could influence the response, but it is not of interest. It's not explicitly of interest. In brackets. That variable is considered a block. That variable is considered a block or a blocking variable. That's really, really similar to stratification, right, in the observational data column, right? And so blocking, right, is kind of the next level of experiments, right? Just like stratification was kind of the next level of observational data collection. And so that's why it's optional, and I'll say kind of similar to stratified random sampling. For example, let's see if I've got it pulled up here. There's one I wanted to do here. There's one with the lights and, oh yeah, here. Oops. Which I thought was kind of interesting. So a study is designed to test the effect of light level on exam performance of students. Usually we don't like to do experiments on students, but it's interesting. And as long as, you know, there's no impact on their grades and things like that, you would get ethics approval. So if I wanted to do experiments on you guys, I would have to go to our research ethics board, plead my case, and say, oh, it wouldn't change anything for them, right? But that's hard to get approval for. I know. It's like they care about you or something. So a study is designed to test the effect of light level on exam performance of students. The researcher believes that light levels might have different effects on people who wear glasses and people who don't. So they want to make sure both groups of people are equally represented in each treatment, right? And so the treatments are fluorescent overhead lighting, yellow overhead lighting, and no overhead lighting, only desk lamps. Oh, it sounds so cozy. We have to think about, in this case, what's the response variable? Kind of tricky, right? So the light level on exam performance, right? So exam performance would be the response variable. That's what I'm ultimately interested in. Exam performance. The explanatory variable, right? We're interested in the light level on exam performance. Right? And so we had the light, yeah, they're calling it light level. The light level, oops. And it has 3 levels, right? Fluorescent overhead lighting, oops, I'm not in pointer mode. There, fluorescent overhead lighting, yellow overhead lighting, and desk lamps, right? No overhead lighting. You get some lighting. Although it'd be interesting if we incorporated the 4th, right? No lights at all, but maybe that's where the ethics board said, no, you can't do that. Although we kind of tried it, pseudo tried it last day with no lights on. So the light level, and there are 3 levels here. But I sense I'm out of time. What's the blocking variable? We're not interested in does glasses make a difference, but they suspect that, okay, if you have glasses, then there's glare and things like that that you're dealing with. And so then you'd want to incorporate that, but you're not analyzing it, right? You're just grouping people just to see if there is a difference. And so the blocking variable is going to be the glasses. And do or don't, so 2 levels. All right. Leave it there. If you have any questions, let me know. Otherwise, I'll see you on Thursday.